Good afternoon, friends. Today is the second lecture on small angle neutron scattering. First, under HBNA webinar. Unfortunately, that lecture was also not there and it went into HBNA Students Forum. Now it is available there. So I requested Dr. Aswal to tell you. I think he is that small angle neutron scattering nothing but a diffraction technique only at small angle, and since it is small angular small q, it's regarding larger or mesoscopic structures, which he emphasized last time. He will also tell you once again, and then he will carry on with this issues with small angle neutron scattering, where we don't talk in terms of coherence or incoherent length, but length densities. Densities. We're talking about densities and not just atomic coherence length, and he will come to that shortly. I'll request Dr. Aswal now to come and deliver the lecture.
So, hello everyone. So, the last lecture was on theory of small angle scattering, and today I'll be talking about contrast variation in small angle scattering. And as Dr. Basu said, that I should little bit recollect what was told in the last lecture. So, in the coming slides, I will also talk about what was discussed in the last lecture. So, the outline of this lecture will be like this. So, I already said in last lectures that the contrast variation is important in the case of small angle neutron scattering, and that is what makes this technique unique compared to other complementary techniques like microscopy techniques. And then the good thing is you will have many ways to change the contrast in the system. Contrast means to simplify the system. So there will be many ways in the case of a small angle scattering by which you can simplify your system. And these are named as isotope contrast variation, spin contrast variation, magnetic contrast variation, and also combining small angle neutron scattering with the small angle X-ray scattering and anomalous small angle X-ray scattering. So what I will be doing is that a little bit talk about all these techniques, but the most commonly used in the case of small angle neutron scattering is the isotope contrast variation. So I will show some examples on this technique of isotope contrast variation. So let's recollect what was taught in the last lecture. So the small angle scattering is looking at length scale, which are of nano length scales, much larger than atomic structures. So typically in the range from 1 to 100 nanometer. And it is looking for the structure of inhomogeneities in the system. For example, if you have a colloidal systems where you have these particles dispersed in the medium, and for such system, you can write your scattering intensity by this kind of expression, where n is the number density of the particles. So obviously, if you have more particles in the system, your scattering intensity will be more. And then interestingly, it is a square of the volume of the particle. So many times, if you have very small particles, you don't see it by small angle scattering here because your intensity also is decreased drastically. So that is the region that if you say that the small angle neutron scattering, it is very difficult to see sizes below 1 nanometer, and it is because of this region that your scattering intensity will be very, very low. And then the functionality is decided by these two terms. PQ is intraparticle structure factor, which is the square of the form factor. So sometimes just call as a form factor. And then another is SFQ, which is interparticle structure factor, which is the Fourier transform of pair correlation function, and just call as structure factor. So these two terms will decide the functionality of the curve. And then this term, which is the topic of today's lecture, is the contrast term actually. So rho p minus rho m is square. And you can clearly see that if you have scattering line density of the particle equal to the scattering line density of the medium, then you can have a zero scattering intensity. Unfortunately, with many techniques, you cannot change this term. And the advantage with the small angle neutron scattering will be that you can change this term, and that's called contrast variation. So basically, the things which are seen with the light, if you want to become invisible, it's not easy because you cannot match your refract index with that of the air. But you'll see in the case of neutrons and also X-rays, you can change this term and make invisible visible and vice versa. So once you have these equations, then as I said in the last lectures, you can get a number of information about your system of interest. For example, you can get number density and volume fraction by combining N and V. Then from contrast, you can get the composition of the system. And from the form factor, you get the information about shape, size, and size distribution of the particles. And from a structure factor, you get the information about the interaction and ordering. So if you are interested to get these kind of information for your system at nano length scale, you can use a small angle neutron scattering. And what this slide shows is typical functionality of form factor and structure factor. So form factor is monotonically decreasing as a function of Q, and this width decides the size of the particle. So it's reciprocal to the size of the particle, this width. So the larger particle will have a narrower form factor. And also the functionality of your curve will be different for different shapes of the particles. So it's very important to look the shape and size of the particle. And then your structure factor will look at short range and long range order in the system. But most of soft matter systems or the systems which are studied in small angle neutron scattering, they will have short range structures where your structure factor shows few maxima of decreasing amplitude. So this is first nearest neighbor, and which will come at 2 pi by d, where d is the distance between the particles. So these are typical form factor and structure factor for a system at nano length scales. So the Q range would be up to, let's say, from 0.01 to 0.2 angstrom inverse. And what does this mean is that if you have a dilute system, for dilute system, your structure factor will be 1. So this will be your structure factor 1 for the dilute system. But when you have a concentrated system, then both of them will have the contribution to the scattering intensity, and the scattering intensity is the product of these two terms. So that means when you multiply S of Q with P of Q, mostly what you see is the first peak, which is called correlation peak, and other peaks, they get multiplied by the small contribution from the form factor at higher Q values. So they usually are not seen unless you have a long range order in the system. But there also, the later peaks coming at higher Qs will have less intensity, and this is because they get multiplied by the form factor of the particle. So these will be the typical scattering patterns you see in the case of small angle scattering. So why this technique is popular? This technique is popular, as I said, because you can simplify the system. And how do you simplify the system? That is by varying the contrast. And this term, which is the square of the difference of scattering length density of the particle and medium, is the contrast term. And how do you change this? So to change this means you can make invisible. So you have a particle which is invisible in the system, but by varying this term, you can make it visible. And also vice versa. So sometimes if you don't want to see a particular component, that also you can make invisible like this, going other way. And then many times you work on systems which are not simple systems. So multi-component system or complex system such as this core cell structure, where you want to get information about both core and the cell. And the advantage with the contrast variation is that you can simplify this core cell structure just as core or just as cell. So when you see just as a core, you only have to get the radius of this core. And when you see it as a cell, if you already have got the radius of the core, you get the thickness of the cell. So you can see, you reduce the number of parameters and you can get the reliable information about the system. So this thing can be done with the neutrons and X's, or combining these two tools. So in the case of neutron scattering, how do you vary this contrast? How do you simplify the systems? So there are three important techniques which are used for this purpose. First is called isotope contrast variation. And this works because, as you know, that neutrons are scattered by the nuclei. And for isotopes, because they will have different nuclei, they can have very different scattering lengths, and that's what happens in the case of hydrogen and deuterium. So they have very different scattering length density. So you can see that magnitude as well as signs are different. And when you have isotopes, that means that most of your properties will be similar. So there will be some changes, but most of the times you can neglect those changes because they will not be much. But for neutrons, you can change the contrast drastically. So if you have different scattering length densities, the corresponding different, they will have different scattering length densities, and this term can be easily varied. And when I say that this technique is used widely in the field of soft matter and biological systems, and you know, most of the systems there are heterogeneous, and that's why this technique is very, very popular for these fields. Another contrast variation technique which is useful and is used is because you have neutrons are fermions, so you have it's a spin half particle. It has two states, plus and up and down. And also what happens is the scattering lengths for these two spins is very, very different. So for example, in the case of hydrogen, you can see this number are even larger than what is for the isotope. So in principle, if you can make use of this technique, it will be much more powerful than your isotope contrast variation. And in fact, there are groups who make use of this technique. Then only, as you may have learned, only the neutron is a right probe to look at the magnetic structures, since it's a small magnet, and that you can make use also small angle neutron scattering to look at magnetic structure as well as nuclear structures. And what you make use of in the case of magnetic contrast variation is polarized neutron. So polarized neutron means you can measure scattering for two states, plus and minus, or up and down. And in that case, your magnetic contribution gets multiplied by the nuclear contribution when you measure the difference of the scattering intensity for plus and minus. So that means if you have weak magnetic contribution, which is the case in most of the times, then it gets multiplied by the strong contribution from the nuclear part. And that way, when you multiply small number by large number, so you can enhance. Which is used and also easy to use is the isotope contrast variation. And I already said this is very popular for hydrogenous samples. For hydrogen and deuterium, your scattering lengths are very different. So how you make use of this technique to simplify your system in the case of contrast isotope contrast variation? Work for the small angle neutron scattering. But if you know about small angle neutron scattering, saying this constituent. For that, you should always prepare a deuterated solvent so that this visibility is enhanced. And then you can simplify and since you have H2 and D2, which have very different scattering length densities, you can mix them in a ratio to get a scattering length density which is between them. So you take a ratio of H2 D2s scattering length density of solvent with the cell. So then only you see the core part. And in next different mixture of H2 D2, you can take a scattering length density where your scattering length of your solvent will be same as that of food, and then you see the cell. So you can simplify it as a core or only as a cell. And in this case, you are changing the solvent, so it's called external contrast variation. But you can also do internal contrast variation. So you can also deuterate your the core, you will only see the cell part. So this is called internal contrast variation. So if you have a chemistry or you sample, this one is preferred. This one is preferred because in this case you will have a low incoherent background. So when you have a deuterated solvent, which is in larger amount in the sample, so you are in. So internal contrast variation is preferred also in international contrast. So here I just show how the scattering length densities are calculated. And as I said that at the length scale of interest in the case of a small angle neutron scattering, you don't see the individual atoms and molecules. So in a molecule, you average this over all the atoms present in the molecule. So for example, you want to calculate the scattering length density of water. So you have 2 hydrogen and 1 oxygen. So you will sum over this scattering length over these atoms and divide by the volume of the H2O molecule. And all this is available in the website to know the scattering lengths of hydrogen plus scattering length of oxygen, and then if you put the values, you get this one. And then if you know the density of your molecule and molecular weight, you can calculate the volume from and volume of the, and you can see this is the scattering land density of H2 is negative and small value. And same thing when you do for D2O. Your in this case total scattering length for 1 unit comes out to be this, and the volume comes out to be this, and then the scattering land density is this one. So you can see the scattering land density of polymer, which is hydrogenous, is this one, 0.61 into 10 power 10 centimeter minus 2. The scattering length divided by volume, so unit is centimeter minus 2. Now let's find out how good is D2 as a solvent or polymer when you want to do small angle neutron scattering. So the contrast term is the square of the difference of scattering length densities, which comes out to with this value. And when you dissolve this polymer in D2O, then your contrast is this one. So you can see this is about 25 times larger. So, and your scattering intensity is proportional to the contrast term. So by preparing your hydrogenated polymer in D2O, you gain intensity by 25 times. And moreover, your incurrent background will be much less now, because you see incurrent background for hydrogen is very, very high compared to deuterium. So it's not only the contrast you enhance, but also the incurrent background is suppressed. So that is why, so whenever you have a hydrogenous component and you want to see this particularly by neutron scattering, you should always prepare it in deuterated solvent, and you increase the contrast as well as you decrease the incurrent background. So what this slide shows is scattering length density calculation uh, uh, for some of the systems. For iron, for example, it's very high, 7.97. Copper again quite high. Aluminium, it is lower side. Titanium, it is negative. Manganese minus 2.90. Iron oxide again very high, 6.97. But if you see these scattering length density as compared to, let's say, if you want to see these particles dispersed in water or heavy water D2, then if you I prepare iron oxide in now D2O, so they are very close, so it will not work. So to see iron oxide in water, you have to prepare this in H2 actually. So like that. So what does it mean is that whenever you want to do a small angle neutron scattering, it is better to have some idea about the scattering length density of the component in your system, so that you know which matrix or which solvent will work for your system. So PO in D2 gives good contrast, but iron oxide in S2 gives you good contrast, and same is copper with manganese. So copper is 6.6. If you have manganese, you will have a very good contrast. So in fact, you may have heard of polymer melt, like which is used to form the tires of vehicles. So these have the polymers which are entangled with respect to each other, and it was not known that what kind of conformation of an individual polymer will take in a polymer melt, because they are entangled with each other. It's very difficult to see one individual one. How does it take a conformation in the melt. So there were about 3 to 4 different models proposed for the conformation. But the experimental verification of this conformation only came when small angle neutron scattering uh, was made available. So you can see this technique came in the beginning of 70s. So this was one of the first work to look at the conformation of polymer in the polymer melt. So basically, what you do is you have a hydrogenous polymer melt and just mix the same polymer amount in a small amount, let's say 1 weight%, and mix it homogeneously. And then if you do the neutron scattering, you will have a strong contrast for this hydrogenous polymer, which is in a small amount. And then you can see exactly what is the conformation of this polymer. It is like this. I mean, if you go to a school where you have hundreds of kids wearing same uniform and you want to search a particular kid, it's very difficult because they will look similar. But if there is a kid who has birthday that day and he's wearing different uniform, different clothes, then you can immediately find out wherever he's either playing or in the class or wherever. So it is like this. So you give different color to this polymer compared to the rest of the change, and then only you see the conformation. So your scattering will only coming from this deuterated polymer compared to this thing. So that was first experimental verification, and then they could find out that it is a random coil conformation of the polymer. So amongst 3-4 different models, so random coil conformation of the polymer was confirmed experimentally by small angle neutron scattering. So this contrast variation is very popular in biological samples because when you talk of biological samples, you have these different components coexisting in a system, lipid, protein, and nucleic acids. And you want to separate and see how they are distributed in your biological system. And good thing is that since their chemical compositions are different, so you differentiate them because their chemical compositions are different. And different so much that if you take D2O H2O mixture, so you will have you can contrast match these 3 components at different percentage of D2O in H2O D2O solvent. So for example, lipid, if you have 13% of D2O in H2O D2O solvent, so your lipid will be invisible. So your scattering land density of lipid will become close to that of the solvent. And in the case of protein, it is 42%. And for RNA, 65%. So if you do the experiment for different percentage of D2O in H2O D2, you can systematically separate these components, and it would be easier to find the complex structure of biological samples. And many of these studies in this field have been carried out using isotope contrast. So one simple example where I have 2 kind of structures simultaneously dissolve in a solvent. So one is this small structure, another is this structure. So this is one surfactant micelles, this is one block of polymer Micelles. Now idea is to know how do they form their structure. So in individual solution, it will form this kind of a structure, and this will form this kind of a structure. But what happens if they mix? So one possibility is they will form their own structures like this, or another possibility is that they can form a mixed structures like this, because they have some common parts, hydrophobic and hydrophilic parts. So they can also form this kind of mixed structure. So how do you verify? Contrast variation is small angle neutron scattering has the advantage because you can simplify some of the components. So what I do is I take a deuterated solvent and also take a deuterated this component. So if that is the case, then if I had this situation, then this is contrast match, so I will only see this. So my scattering, my sample will go from this to this phase. So if I am seeing by the neutrons, in this case I had two contributions, this and this, and now I will have only one contribution. So I would expect my scattering profile to change drastically, because I am seeing now different composition in the system. But if this is the case, then even though I contrast match this thing, my main composition remains same. So I may not see the drastic change in your scattering profile. So I may see the contrast change, but my structure remains same. And that what you do is verify by doing the experiments, and you could see that at different concentration experiments have been done. The scattering reduced because the contrast is changed, but the profiles are maintained. So here they are normalized. So the experiments confirm this kind of structures form in the system, not of this. But if you didn't have this technique available, then you would have either claimed of this or this. So this is the beauty with the contrast variation is small angle. So how do you contrast match a particular component in a system? So let's say I have in this particular slide, I want to contrast match silica nanoparticles which are dispersed in a water. So they may be visible like they are seen here. So now slowly what I will do is I change the solvent. So this is suppressed, and at some point of time they will become invisible. So they will be contrast matched to the solvent. So if you know the chemical compositions, you can do some calculations and get this kind of conditions, but nothing like verifying this experimentally. So you can verify this experimentally, and for that what you have to do is you vary the one of the component in the solvent, let's say H2O, in H2O D2O mixture, so 25, 30, 35 up to 50, and then basically, you know, your scattering intensity is proportional to the contrast term. And if you take a square root of this, then some constant, and then it will be rho p minus rho s. So if you are systematically changing the contrast, then there will be a contrast point where your rho s will become larger than rho p, and then your square root of I could be negative, and that's how you get. So basically the profile will not change because your system is same, only your contrast term is changing. So you can see you are plotting a square root of I of q with the percentage of H2O in H2O D2O mixture, and you have points on both sides, on below contrast point and above contrast point. And then when you this is a straight line equation, and then where it cuts this straight line cuts x-axis, that is the contrast point. So in this case, we get 38. We get a contrast point, which is 38% of H2O in H2O. So this is experimental verification, and it may happen that when you want to do it from the chemical compositions, you can get a number which is close to this. So always, if you can manage this, it is better to verify this experiment. So once you have you know the contrast match point of your components, you can simplify. So for example, in this case, what you want to do is want to know what is happening when you mix these nanoparticles with some micelles, and particularly when they are similarly charged, you expect them to be non-physically interacting. Of course, individual may be changing structure and interactions, and that you want to confirm. So what you do is you contrast match nanoparticles actually. And once you contrast nanoparticles, then from this system, you take the data. So this system will look like this. And then you see whether it is that of the only micelles actually. So the mixed system and only the micelle individual component under the same contrast conditions and they exactly match. So what does this mean? This means that they do not physically interact and nothing happens to micelles. They remain even though with and without nanoparticles, no structural change of these micelles. And you can also contrast match micelles, and again this system with only nanoparticles you see, and again two scattering profiles match. So again it says they don't physically interact and also nothing happens to the interaction between the nanoparticles. Of course, when I show the results in later lectures, you will see there will be cases where even though they are not physically interacting, you could have depletion interaction setting up in the systems where nanoparticles start interacting. But for this particular system, this does not happen. So this is exactly the same. However, for other case, you could have different situations where these are now nonionic micelles. So here they were anionic micelles, here they were nonionic micelles with anionic nanoparticles. Here there is a possibility that they can get adsorbed on the nanoparticles. As a result, when you contrast match the nanoparticles, and then again the same situations when you have nanoparticle with surfactant micelles and only micelles. Now micelles only are very different than micelles when mixed with nanoparticles because their distribution is changed. So in earlier cases, if they were not interacting with nanoparticles, they would have looked like this. For that, your pattern is like this. But now since they have redistributed themselves and interacted with the nanoparticles, and that is seen here, where you get very different scattering patterns, which is from the now Micellar adsorb on the nanoparticles. And what about the nanoparticles only? So now you contrast match these micelles and only see the nanoparticles. So they are same. So nothing happens to the nanoparticle. Only it's the micelles which they are redistributing themselves, and nothing is happening to the nanoparticle. So there is no change. So this kind of detailed information about your complex structures can only be obtained when you have this flexibility to vary the contrast. And when you vary the contrast, you simplify your scattering terms. For example, if let's say nothing was contrast match, so what would have happened was if you had these micelles adsorbing on the nanoparticles, so your scattering will have four terms actually, from scattering coming from the nanoparticle, then from these micelles, then cross term of nanoparticle and micelle, and micelle. So these four terms, and to model them and get a reliable fit would have been very, very difficult. So you can have different combinations giving you the same fit. So to get a reliable fit is very difficult. But once you contrast match this part, the nanoparticles, then there will be no scattering from nanoparticles, so that will vanish. And also there will be no cross term from the nanoparticle with micelles. So only two terms are left, that are from the micelles and also micelle populations. And that is very useful because now what you are only seeing is micelles. And if from the pure solution you already know the size of this, only what you will get is the information about the micelles, the size of the micelles and how many of them are adsorbed on the nanoparticles. So just this figure shows the adsorption of these micelles for different size nanoparticles. These are 8, 16, 27 nanometer. And how many are adsorbed actually. So when you have a small size, this number is small. And when the size is increased, your number of adsorption is also increased. And but the fraction of adsorbed micelles decreases because you know when the size increases, average surface area of the nanoparticle also decreases for the given concentration of nanoparticle. So this was about isotope contrast variation, and as I had said that there are other techniques which are also useful to vary the contrast, and this one is spin contrast variation. And in principle, this is much more powerful than isotope contrast variation, because this is the change of scattering length you see when you change the isotope. You go from hydrogen to deuterium. But if you are within hydrogen and you can vary the spin contrast, then you can see the change 10.82 plus to minus 18.0. Changes are varying. And basically, this is the expression you can write. So what is done in spin contrast variation is you have to polarize the hydrogen nuclei or deuterium, whichever you want to do the experiments. And then you take the, so one is the polarization of nuclei. So if you have hydrogen, you want to polarize, so it's a hydrogen nuclei. And then also polarize the incident neutron beam. So plus minus is for the polarization of the neutron beam in this formula. And this P term is for the polarization of the hydrogen nuclei. So this is not difficult actually. To polarize a neutron beam is not difficult. So you may have seen this in polarized neutron diffraction. But what is difficult is polarizing the nuclei actually, because magnetic moment of nuclei is very small. So in principle, you'll need very, very high magnetic field and very, very low temperatures to be able to align these nuclei. And the method which is used is dynamic nuclear polarizations, where with the help of electron polarizations, you polarize the nuclei. But still, you need very high field of the order of 2 to 3 Tesla and low temperatures around 1 to 2 Kelvin. So you can see, I mean, to get these kind of sample environment uh, uh, is not easy. And that's why, although this technique is very useful, but its application has been very limited. So only few groups who can afford to get these kind of sample environments, they make use of this technique. But as I said, it's very useful. Even more, you can produce more contrast than what is getting the isotope contrast variation. Then another technique which I had talked about uh, contrast variation small angle neutron scattering is polarized small angle neutron scattering, which is useful for magnetic system. So as you know, neutrons, they are scatter. You will have nuclear scattering as well as magnetic scattering. So if you have a magnetic system and unpolarized neutron, this is the scattering law. So nuclear contribution and magnetic contribution. And so to see magnetic contribution, you have to apply field to the system so that your moments are aligned. So alpha is the angle between the direction which you are measuring, the direction of Q and H. So you can see, so when alpha is 0, so you will have only this contribution. And when alpha is 90, you will have maximum contribution from magnetic part, the scattering intensity. But if this term is very small, then it will be very difficult to measure this over the nuclear part actually. So mostly this to get your magnetic contribution from this will be less precise. However, you can make it more precise when you use polarized neutrons. So plus state, this is the scattering law, and minus state, this is the scattering law. And what is important is when you subtract actually I plus minus I minus q, you get a term where your nuclear scattering is now multiplied with the magnetic scattering. So even though you have a weak scattering from the magnetic part, it gets multiplied nuclear part. So this term actually, so you are not directly measuring FM, but you will now measure FM through this term actually. So this gets enhanced actually. So in that case, whatever contribution for either cases. Even when you add, it's isotropic. But when you subtract, actually, now you start seeing this term actually. So this term will be 0 when alpha is 0. And this term will be maximum when alpha is pi by 2. So you can see only to know that there is magnetic contribution. You can only come from this term actually, I plus minus I minus. Because this is a term which is directly proportional to alpha, sinus square alpha. And once you see this kind of pattern, then you can get the magnetic contribution from the sample as well as nuclear contribution. So far I talked about 3 different contrast variation techniques using neutrons alone, which is isotope contrast variation, then spin, and then. But you can always use neutron with X-rays because, as I said, that these 2 techniques in principle are very same, only different. You will see neutron and X-ray sources are at the same place. You will see this in Nobel and also in Fliegen, Switzerland, where neutron and synchrotron sources, they are close to each other, so that those who want to use both the technique, because as the Z increases, so you are high elements. And the advantage with neutron is that unlike X-rays, you can see the low Z elements. So if you have high Z and low Z components in your system, using these 2 techniques will be that so for example, in this case, you have the same system and you are seeing it by neutron and X-ray. And first of all, you see that their scattering patterns are very different. And this is because neutron and X-ray, for the same systems, they are seeing it very differently. So neutrons, because your scattering is from hydrogenium component, it sees the core of this structure. This is Micelle, core of this Micelle actually. On the other hand, X-ray doesn't differentiate, but it is more for higher Z elements. So this difference is coming because in the case of neutrons, you only see the core. So it means you already can measure the core dimensions or core structure from the neutron. And that information, if you have already incident energy or wavelength, you can do anomalous small angle X-ray scattering. What is anomalous small angle X-ray scattering? What is done is energy of the incident X-ray beam is very near the absorption as of an element to be examined. So let's say for a particular element you want to change the contrast. So what you do is vary the energy of your incident X-ray near the absorption as of that element. And what happens when you go near the absorption as your absorption is increasing. So you can write a scattering length, the 2 parts, real part and imaginary part. So real part is so here the absorption as your energy is such that you can knock out the electron from the atom. So there your absorption will increase and your scattering length is decreasing. And how do you differentiate different elements, because their absorption as are very different. So for example, iron, cobalt, nickel, copper, they are neighboring elements, And if you just want to see by common X-ray, it will be very difficult to differentiate because they will mostly scatter same. So if they scatter same, it will be very difficult to differentiate. But if you can vary the energy near the absorption edge, so these are in keV, and energy you can vary in few electron volts with that precision. Let's say you have to see particular component. So let's say you want to see cobalt, then you vary the energy near the Fe. So that will be contrast match, and you only get the scattering from the cobalt. So very powerful technique to look the system which otherwise are not possible to see. So I now give example again of Micelles. So as I said, with Neutron and X-rays, you can come to know see it as a core cell structure. So what I'm trying to look here is counter condensation. So what happens basically when you have these Micelles formed, so they will have these charges at the surface, and unlike NaCl where both sodium and chloride are dissociated, since these positive ions are at the surface, they will attract these counterions actually. And the final property of this structure will be decided by how much of these counterions are condensed, because these macroions now can attract these small counterions. And we want to see how these counterions are condensed, at the surface. And to see that, as I said, that you can make use of neutrons and X-ray together, because neutrons will see this core, which is mostly hydrogenous. And now X-rays can see these condensed counterions, because, for example, in the case of bromide, since it's a high Z element, so you will have a very good scattering. So that's what is seen in the case of SANS. This is the pattern. And this hump is coming because of the cell structure now seen by the X-rays. And you can see the scattering line density variation for case of neutrons. Only you see mostly the core actually. And in the case of X-rays, you start seeing these counterions actually, which are not visible in the case of neutrons compared to the core, because there is a very strong contrast. So basically, what happens? So these condensed counterions, if you want to see, if I want to verify, because there has been a lot of work in this topic, where bromide, chloride, iodide, these counterions, they behave very differently. So as a result, the phase behavior of these structure is very, very different. So just to see whether you can identify the condensation of these counterions by anomalous small angle X-ray scattering. So this is the bromine edge, and what you do is you vary energy near the edge actually, and then you can see your scattering profile is changing because the contrast for the bromide is changing. However, if you take the same system with chloride counterions and now you change the energy near the absorption edge of bromide, same energy basically, so you don't see any change. So what does this mean is that by changing the energy near the absorption edge of bromide counterion, you are changing the contrast for bromide, right? And hence the scattering pattern is changing. And if you want to differentiate bromide from chloride, you can use this concept of anomalous small angle X-ray scattering. So this is how you verify in the research problems. So first is when you have these counterions, bromide and chloride counterions. So there is selective condensation. So particularly if you take this system CTABr and add some bromide salt, you have a strong change in the scattering pattern, where you have these spherical structures going to rod-like and very large structures actually. And this scattering buildup is because they form very large structures. While in the case of chloride, actually nothing happens, because although their bare size is smaller than the bromide counterions, but because of larger hydration of these chloride counterions, they are much bigger in size. In that case, they are not able to condense. So in that case, you don't have a strong buildup of scattering intensity as seen in the case of bromide counterions. But what you want to do is you want to see that bromide is still have the similar effect for the original chloride counterions actually. So what is happening? So whether your chloride counterions are completely replaced by bromide or there is exchange, that you want to verify. So for that, this technique is the unique technique, anomalous small angle X-ray scattering. And you have this system CTA, BR, KCl. You want to see whether there is exchange of counterions or there is a selective condensation, and you do the anomalous small angle X-ray scattering, vary the energy of incident X-ray near the absorption edge of uh, bromide counterions, and then you see some change. That is because there are some bromide counterions there. But in the case of chloride counterions, original chloride counterions, now if you add bromide counterions in the system, so you get a system behavior which is similar to this system. So these two systems, this and this, now behave same. What does this mean? This means that they have now similar kind of configuration of counterions. That's why their profiles are same. And so what is verified by this experiment is that chloride counterions are exchanged by bromide. So this again you can only verify by doing the contrast variation experiment, which is anomalous small angle X-ray scattering in this case. So to summarize all this work, I have one example where you will see that when you do different techniques, you get different numbers. But if you know what you are doing and if you can do the contrast variation, you will get the complete information about the system. And basically, this example is on a magnetic fluid, which are nothing but the suspension of magnetic particles in carrier liquid like water. And since these are magnetic particles, if you don't do anything with these magnetic particles and just want to disperse them, they will aggregate because of magnetic interaction. So what you do is either provide some charge on them or provide a coating of some polymer or surfactant around them so that you can provide a steric repulsion. So basically, in this example, what you have is a double coating of surfactant around the magnetic nanoparticle to avoid their coagulation against magnetic interaction. And now this system, if you study by dynamic light scattering, where what you are looking basically is the diffusion of these particles, and from there you get the diffusion coefficient, and then using Stokes-Einstein relations, you can get the hydrodynamic size of the particle. And if you measure that, that comes out to be 10.5 nanometer. The same system, when you study by small angular X-ray scattering, you get just one size actually, 4.8 nanometer. It's has some polydispersity. But when you do small angle neutron scattering with two contrast conditions, one when your particles are contrast matched, and second when your surfactant coating is contrast matched, then you get two numbers. One is 4.8 nanometer, another is 4. So if you want to understand this after doing these three measurements, how do you understand them? So you will start with the small angle X-ray scattering. As Fe3 is the high jet component compared to these carbon hydrogen surfactant molecules. In the case of small angle X-ray scattering, you mostly see this core actually, which is 4.8 nanometer. So in this structure, you only get the core size of the particle. And when you do dynamic light scattering, you see everything, core, cell, and also the hydration which is attached to this particle. So which will be larger than the overall size. But when you do small angle neutron scattering, you get the core size, which is consistent as obtained by SAXS, plus you get the cell thickness of this surfactant coating. So that only you can get when you use contrast variation in small angle neutron scattering, and also you can get hydration information from dynamic light scattering. you can simplify small angle neutron scattering if you already have some information on the small angle X-ray scattering. So only the suggestion would be that you should use as many as technique, because at the end, information from these scattering techniques, they come from the model, you assume, and the model will be more reliable when you have use as much as information known about the system. And for that, it is always advisable to use as many as techniques available to you. And further advantage, as I already told about the neutron, is that you can separate nuclear and magnetic scattering. And in this case, from this term, which is the difference of the scattering for two states, and as I told that your weak magnetic scattering gets multiplied with the strong nuclear part. And then you can see here, I mean, these are the finally derived contribution for nuclear scattering and magnetic. So about 2 order less magnetic scattering, and you see the error bar. I mean, they have been measured quite precisely and without any incoherent background. So this is the beauty with the contrast variation, that very weak component can be separated from the strong contribution using contrast variation, magnetic small angle neutron scattering. So to summarize, what I would say is small angle neutron scattering is popular because it provides easy possibility to vary the contrast to characterize complex heterogeneous system. And then SANS can probe both non-magnetic and magnetic samples. In particular, polarized SANS can be used to separate weak magnetic scattering from nuclear scattering. And then as neutron and X-ray interact differently with matter, the combination of SANS and SAXS can be utilized to prove both the low Z and high Z components in the system. And that is the reason these days when you see neutron source, you also see a X-ray source next to neutron source. And then if you can, spin contrast SANS and anomalous SAXS have the advantage where use of other contrast technique is limited. So if you think there is a possibility, you should also think of using spin contrast SANS and anomalous small angle X-ray scattering. Thank you.
We'll wait for a few minutes for questions. I hope there will be questions. Yes, please. Intra-particle interactions. Can I answer this? So this is basically, these are conglomeration of particles. So take an example which Dr. Aswal was using. For example, it's a micelle. When you see, it has got a head which is hydrophobic and tail which is hydrophilic, or vice versa. So they combine. So here it is basically uh, trying to keep, let us say, water out, will give it a shape which is maybe spherical, maybe cylindrical, maybe ellipsoidal, and that's what you see here actually. So not one surfactant molecule, but when they form a micelle, a conglomeration of them. So this is, you can say, this is steric repulsion. Sometimes it can be a charge which can make the people to come together or go away together. So all this, there are various kinds of interactions which will make these conglomerations. And you are looking at this not at the atomic level, but a conglomeration of particles, molecules, which you see in the length range, as Dr. Aswal said, in say nanometer to hundreds of nanometer. That means tens of angstrom to 1,000 angstrom. Please keep it in mind. You are talking, we are talking in terms of conglomerations, particles which are in a medium, contrast. So this is away from diffraction which you did for atomic structure. This is also a diffraction technique, but a much lower angle at a lower Q value. So quantum mechanically, twice pi by Q gives you the spatial resolution, which we have intentionally made worse. So you are seeing these conglomerations, and today he talked about contrast where you saw the, but especially I will request you to pay attention that how you can make part of a large particle visible or invisible by matching the contrast between H2 and D2O. The in nuclear neutron interaction, H has a different scattering length compared to deuterium. The chemistry remains same, but the contrast is so good that you can mix D2 and H2 literally in a beaker and make different parts of a particular particle visible or invisible. And same thing goes on to when you do a spin variation, you could see that. Any other questions? Property of particles will not change. This is basically visibility of the particle will change. So we will talk about visibility vis-a-vis the small angle neutron scattering, because the particles are immersed mostly in a medium. So if this particle is immersed in a H2O D2O medium, mixture medium, then the visibility of the particle will be as if you make some parts invisible. He used the term, Dr. Aswal used the term visible, invisible. So he can make certain part glow up or come into visibility, some parts go away from visibility. Counterion thickness.
So as I said, if you want to look at the quantine condensation, then you have to combine neutron with X-ray, because neutron will look at the hydrogenous part, that is the core of the micelle. And once you know that, then you can use X-ray, and X-ray will see core cell structure. And then from that modeling of that data, what you get clearly, what I showed. So this one actually. So if you see the case of neutron, you have this kind of pattern, blue curve, and in the case of X-ray, you are seeing this thing. So mostly this hump is coming because of the cell structure seen by the X-rays. And then what you model is this kind of scattering length density distribution. So in the case of neutrons, so this is mostly, you see, where scattering depends on the difference of uh, scattering length density of components with respect to medium. Or in this case, this difference is maximum for the core. So that's why mostly the core is visible. But in this case, you can see you have clear contrast for the countines compared to the medium and the core. So what is visible? So this part is basically coming from the condensed counterines, and that gives you the thickness of this thing. So for example, in this case, it was found to be around 5 angstrom thick around the micelle. So the next lecture on data analysis methods will be on Friday, 8th of January.